evening, dear students. In the previous lectures, we have shown that how operational amplifier circuits are used to provide AC oblique DC amplification. Perform such mathematical operations are summing, or we can say summing amplifier, averaging amplifier, differentiation, and integration. And it also provides a very high input impedance. In this present lecture, I will explain how to design active filter using operational amplifier. In this lecture, I will begin with the analysis and designing of basic and expensive filter types, and then in the next few lectures I will also discuss about the various oscillator circuits using operational amplifier. First of all, I would like to concentrate on how to analyze and design of basic and inexpensive filter types. As we know, electric filter is sometimes also known as frequency selective circuits that passes a specified band of frequency and blocks or attenuates signal of frequencies which lies outside this band. Or we can say a electric filter is nothing but it is a electric circuit that passes a specified frequency and attenuates or blocks the rest of the frequency outside that particular limit. Filter may be classified in a number of ways. Number one, analog and digital filter, passive and active filter, or audio or radio frequency filters. Analog filters, they are designed to process analog signal, whereas digital filters process analog signal using some digital techniques. Depending on the type of elements used in their constructions, filter may be classified as passive or active filters. Element used in passive filters are resistors, capacitors, and inductors. And whereas in active filters, the elements used are transistors or operational amplifier in addition to resistors and capacitors. Or broadly speaking, we can say that the passive filter contains the element such as resistors, capacitors, and inductors. Whereas in active filters, we don't use the inductor, we use operational amplifier or transistor in addition to resistors and capacitors. The type of element used dictates the operating frequency range of the filter. For example, RC filters are commonly used for audio or low frequency operations, whereas LC filters, that is inductor capacitor filters, or sometimes the crystal filters, are employed at high frequency, or we can say radio frequencies, especially because of their high Q value. That is, Q stands for quality of figure or figure of merit. The crystal provides more stable operations at high frequency. So we can say the active filters which are designed using op-amp along with the resistors and capacitors, they are broadly used in audio frequency or low frequency operations, whereas filters with high value of Q, they are used at higher frequencies because they provide more stable operations, or it provides stability at higher frequencies. And active filters offers the following advantage over a passive filter. Number one, gain and frequency adjustment flexibility. Since op-amp is capable of providing a gain, an input signal is not attenuated as it is in passive filter. In addition, active filter is easier to tune or adjust. Means we can adjust the gain of the op-amp just by changing the feedback register and the input register in the op-amp configuration. Second point is no loading problem. Because of high input impedance and low output resistance which is provided by the op-amp, active filter does not cause loading of the source or the load. Or we can say we can connect the first stage to the next stage without the effect of loading because operational amplifier offers high input resistance and low output resistance. Third is cost. Typically, active filters are more economical than the passive filter. This is because of the variety of cheaper op-amps and the absence of inductors. The cost of active filters are less as compared to passive filter because more and more cheaper op-amps are available in the market, and secondly there is no use of inductor, that's why they are cheaper in nature. Although active filters are most extensively used in the field of communication and signal processing, they are employed in one form or another in almost all these sophisticated electronic systems. Radio, televisions, telephone, radar, space satellites, and bioequipments are few systems that employ active filters. Or we can say in almost all the current electronic system, we use active filter instead of passive filter because of the above three advantages. The most commonly used filters are low pass filter, high pass filter, band pass filter, band reject filter, and last is all pass filters. Each of these filters uses op-amp as an active element and resistor and capacitors as passive element. Although 741 type op-amps work satisfactory in these filters, high-speed op-amps such as LM318 or ICL8017 improve filters performance through their increased slew rate and higher unity gain bandwidth. So we can use high-speed op-amp if we required better performance as compared to 741, which works satisfactory in the designing of active filters. Figure 7.8.1 shows the frequency response characteristics of all the five types of filters. The ideal response is shown by a dashed curves, while solid line indicates the practical filter response. A low-pass filter has a constant gain from 0 to a high cutoff frequency, which is denoted by small f capital H. H stands for high cutoff frequency. Therefore, the bandwidth is also fH. At fH, the gain is down by 3 dB, or we can say at high cutoff frequency, the gain decreases by 3 dB. After that, that is if the input frequency is greater than the high cutoff frequency fH, it decreases with increase in input frequency. Means if we increase the input frequency after a particular high cutoff frequency, then the gain of the operational amplifier it decreases. The frequencies between 0 to FH are known as pass band frequencies, means those frequency which are allowed to pass, they are called pass band frequencies, whereas the range of frequency beyond the high cutoff frequency that are attenuated or blocks are known as stop band frequency. Therefore, we can say the passband frequencies are those frequencies which lies between 0 and high cutoff frequency, whereas the stop band frequencies are the frequency range beyond high cutoff frequency. Figure 8.1 shows the frequency response of a low pass filter. As indicated by the dashed line, ideal filter has a zero loss in its pass band and infinity loss in its stop band. Unfortunately, ideal response or ideal filter response is not practical because of linear networks cannot produce the discontinuities. However, it is possible to obtain a practical response that approximate the ideal response by using a special design techniques as well as precision component values and high speed operational amplifier. So we can say that we can design a ideal filter which is practical filter which is equivalent to ideal filter response by using a special technique and a selection of precision component values and using high speed op amp. Butterworth, Chebysky, and Kozer filters are some of the most commonly used practical filters that approximate the ideal response. The key of the Butterworth filter is that it has a flat pass band as well as stop band. For this reason, it is sometimes called a flat filters. We can say that the Butterworth filter, which is having a flat pass band as well as stop band, is sometimes also called flat filter. Chebysky filter has a ripple pass band and a flat stop band, while the Kozer filter has a ripple pass band and a ripple stop band. Generally, the Kozer filters gives the best stop band response among the three. Because of their simplicity of the design, low pass and high pass Butterworth filters are discussed here. Or we can say we will in this lecture we will design Butterworth filter which is having low pass and high pass filters because of their simplicity of the design. In the figure 8.1b, this is the frequency response of low pass filter, high pass filter, sorry. This is the frequency response of high pass filter, in which up to a certain frequency, which is called low cutoff frequency, it will stop the, or we can say, stop the frequency to pass, and after a certain frequency, which is known as low cutoff frequency, the response increases and it remains almost same for rest of the frequency. So the frequency range between 0 to FL is known as stop band, whereas the frequency range beyond FL is known as pass band. This is the frequency response of high pass filter. Next is the frequency response of band pass filter, in which up to a certain frequency, which is known as low cutoff frequency, it stops the gain to increase, and after that the gain increases, and up to a certain frequency, which is known as cutoff frequency, the gain at, attains highest value, and after that the gain starts to decrease, and after the frequency fh, which is known as high cutoff frequency, the gain decreases, and the response, the gain decreases to zero. The frequency range in which the signal, or we can say input frequency, allowed to pass between the range fl and fh is known as pass band, and rest of the two bands are known as stop band. The next is the filter response of stop band filter, or sometime it is called stop, or we can say pass band reject filter, pass reject filter. Here up to FL, the gain remain constant, and after FL it decreases to minus 3 dB, and at a certain frequency the gain attain zero value, and after that it again starts increasing, and the cutoff frequency in this case is FH. The frequency range between FL to FH is known as stop band, because in this range the gain of the filter decreases and it attained a value of 0, whereas the frequency range between 0 to FL, the gain is 1, and after that again the gain attained the value of 1. This is the frequency response of all pass filters, where the phase shift between input and output filter of an all pass filter is by a phase of 90-degree, changes by a phase by changes by 90-degree. The figure 8.1e shows phase shift between input and output voltage of all pass filter. This filter passes all the frequency equally well, that is, output and input voltages are equal in amplitude for all the frequencies, while with the phase shift between two functions of frequencies, the highest frequency up to which the input and output amplitude remain equal is dependent on unity gain bandwidth of the op-amp. This point must be noted that the highest frequency up to which the input and output amplitude remain equal is dependent on unity gain bandwidth of the op-amp. At this frequency, however, the phase shift between input and output is maximum. Before we proceed with the specific filter type, let us re-examine the filter characteristic, especially in stop band region. As shown in figure 8.1 A to D, the actual response curve of filter in stop band either steadily decrease or increase or both with increase in frequency. The rate at which gain of the filter changes in stop band is determined by the order of the filter. We can say the rate at which gain of the filter changes in stop band, it is determined by the order of the filter. For example, the first order filter, whether it is low pass or high pass, the gain rolls off at a rate of 20 dB per decade in stop band. That is for frequency greater than high cutoff frequency. On the other hand, for a second low pass filter, the roll-off rate, or we can say the gain, decreases at a rate of 40 dB per decade and so on. Means if we are using first order low pass filter, the gain rolls off at a rate of 20 dB per decade in stop band, and if we are using second order, the gain rolls off at a rate of 40 dB per decade, and if we are using third degree or three order filter, in that case the gain rolls off at a rate of 60 dB per decade. By contrast, for the first order high pass filter, the gain increases at a rate of 20 dB in stop band and increases at a rate of 40 dB for second order and so on. So in low pass filter, the gain rolls off at a rate of 20 dB per decade, while in case of high pass filter, the gain increases at a rate of 20 dB per decade in stop band and so on. So in the next lecture, I will try to design and analyze the first order low pass filter and first order high pass filter. Till then, bye bye. Thank you. Take care of you.